So, welcome to the last day. After all the week together, today we're going to talk about maritime applications with SAR. And we have today with us Dr. Domenico Velotto. He's coming from the University of Bremen in Germany, where he works as a researcher. And before that, he was doing his PhD in SAR maritime applications in DLR. So today we're going to cover topics like oil spills and ship detection, and also this will include AIS, which, if I'm not mistaken, is Automatic Identification Systems from ships. And so this will be part of integrated applications with Earth observation.
Welcome, everyone. So good morning also from my side. Thank you, Amalia, for introducing me. So today we are talking about SAR marine applications, and particularly oil spill and ship detections. So here is the agenda for today. Yes.
You're seeing the comments. Swap because we're seeing the comments.
You see the comments.
Oh,
okay. Then.
Because you were in presentation mode now.
Yes. Right? Yes.
I know it happened yesterday and the teacher fixed it, but I don't know how he did it.
I also don't know because...
Does anybody know how to make that change?
Wait, maybe because of Zoom. Yes, I have to not share the total screen, but...
What's the problem?
So they see, instead of seeing full screen, the main slide.
Just stop sharing first.
Yeah, because we share the...
Then share the second screen, not the...
I just share the presentation.
Yeah, but now it's this view only. If you share this, it will not share the presentation. Oh, it's shared. Fine. Good.
Do you still see the comments?
Yeah. Okay. And what if you share the screen then? You were sharing the screen before?
Just stop sharing here.
Maybe just make extended display, not extended duplicate.
No, he needs the notes.
No, I don't need the notes, but...
Okay. Just click on sharing, please. Click. Presentation is not launched, so you cannot share it.
If you share screen and the application.
Okay.
Yeah, but if I...
And now if you click switch to the Zoom, you will see...
Yeah, but I cannot, because if I'm in the presentation mode, I cannot...
Okay, then maybe in presentation mode here, view. Sorry.
Notes.
Slideshow.
Oh.
Slideshow. Sorry, here. This one. And there should be monitor. Use presenters mode. Yes. And then click here. No. Okay. We are finished with the settings in the presentation mode. Now you need to change Windows settings. Not to extend it. Now it should be fine, I think. Launch presentation and save.
Yeah, I should first share and then...
And then you can do it, yeah? Is it better?
No, okay, now it should work, because I don't see it here.
Yes.
Okay, yeah. Sorry for this little technical issue. So I will try to have the two topics covered in the two slots. So we'll start with some introduction about the synthetic aperture radar marine applications. And then there are two fundamental parts that I would like to give you some basic information. So about ocean waves, so how the ocean waves are generated, and some basic concept about SAR polarimetry, because it's some technique that it's commonly used for oil spill and ship detection. And then we go to the topic specification. So the first part is SAR oil spill detection with some information about how oil spill happens and why. Then we have the interpretation of oil spill with SAR. And then I will show you some algorithms using single and multipolarization SARs. And more or less the same structure follows also for the ship detection. So I will also give you some basic information about what is the automatic identification system. And then, yeah, so the interpretation of ship detection in SAR and some algorithms that are commonly used. So general introduction. So on the right-hand side here, you see a map which shows you general classes of what we have on our planet. And you see most of the Earth's surface is water, and is about 70%, so it's quite a lot. And when we talk about Earth observation, so you want to actually monitor also the ocean. So you are monitoring 70% of the Earth. So that's quite important. And because it's a lot, so of course satellites come into handy because they offer an optical a view from above. Then we have also that oceans are important because they provide resources, renewable and renewable sources of energy. So if you think about oil exploitation from the seabeds, and if you think about wind farms, offshores, then you have these kind of sources. And another important point is that 72% of Earth's biodiversity lives in oceans. So that's why you want to protect it, right? How can we monitor the oceans? So, of course, standard techniques. You have in situ measurements. You have ships that are going out and taking measurements, and you have models that can predict how the ocean behaves, how the currents develop around the Earth's oceans. But these are expensive and they are punctual, so it's not always easy to have a good overview about all the oceans. And that's why satellites come into play. Today we are talking about SAR, but these are not the only one used for ocean monitoring. So we have spectral radiometers. They measure the lights in a wide wavelength spectrum, and they are used for chlorophyll content, sea surface temperature, and so on. We have the microwave radiometer that measure the energy emitted in the microwave spectrum, and they are commonly used for, again, for sea surface temperature, atmospheric water content, and so on, salinity. Then we have the satellite, the altimeter, which measures the turnaround time delay of the electromagnetic pulse. And in this way, you can measure the sea surface height, ocean wind, direction, and waves. So then we have the scatterometer that's also measure the scattered energy while scanning the Earth's surface, and is commonly used for wind speed and direction. So it's quite a good instrument. Then we have the infrared radiometer that measure the radiation in the infrared light, and it's specialized for sea surface temperature. And of course, last one is SAR. So you should know by the end of this course what it measures. So it measures the backscatter from the scene that is observed, and we will see now for which applications is used in the maritime domain. So this is a slide which shows you recap of most of the application you can do with SAR. So we have we have oil spill, and you can also monitor seepage. So oil seepage is the what you find in the under the ocean's floor. So it's a way to extract oil. Then there are studies about how the oil drifts. So this is also quite important because in case of an oil spill, you want to predict how the oil is moving, if it's reaching the coast. So you need to take special measurements to prevent it. And there are also ocean eddies that are quite important for current circulation and so on. Then we have the ship detection and the wake. We will see it by the end of this course, what it's about. Then we have the land-water line discrimination. This is also quite important for coastal erosion. Iceberg detection. So I don't have to tell you about Titanic, but that's something that you can do with SAR. And of course, also the ice classification. So that's also quite important nowadays to open new routes on the North passages, because then ships are shortening the travel between the continents. But it's quite dangerous because if you don't know the icebreaker where it has to go, and then it happened that icebreakers were stuck in ice for days, and that's quite dangerous. Then we also wind, so wind speed retrieval, which is also quite important for monitoring typhoons and hurricanes. Here you see an example of a typhoon. Then we have the sea state or ocean waves measurements, so measuring the wave height, the wave period, and this kind of parameter. Wave breaking is when the waves approach the coast and breaks, so that's also quite important. And also some bathymetry, so to study how the bathymetry around some islands are developing. And we have also surface current, so how the current, the ocean current, basically. So these topics, they seem to be totally unrelated, but actually they are not. And nowadays, it's always the case that you want to have all this information together, not just one. Because, for example, there is an oil spill. Then you want to see, for example, maybe who was producing these oil spills. And then you need ship detection. But then, for example, you need also to have the current to estimate how the oil is drifting. So you want to know the meteorological condition around the oil spill, so which wind speed was in place, because as we will see, wind is also one component that moves the oil on the ocean surface, and so on. So these are kind of all together, but today we are talking about the first two, so oil spill and ship detection. And if you are interested, you can find plenty of books about the other topics. And to have some backgrounds before we start on the technical part, I want to first talk about how you can monitor the ocean with SAR. And as ocean waters have high dielectric constant, so basically the radio waves penetration is negligible. So SAR cannot see under the water. You only have so-called surface scattering. So this should be a concept that was that you might already have heard in the basic SAR seminar. And of course, related to the surface scattering, what is important is the roughness. So maybe you have also heard this. And what makes SAR observing the ocean is the roughness. And the roughness is caused by the ocean waves. And here there are some criteria, so the Fraunhofer criteria that tells you how you can discriminate when a surface is smooth or if it's rough, and a basic interpretation what it happens when you have a smooth surface. So basically, a smooth surface, you have the incidence wave that is sent by the satellite, by the SAR, then reflected away from the sensor. And if the surface starts to have some moderate roughness, then part of this energy comes back. And this is what you measure. And of course, the stronger is the roughness, the more you measure. And roughness in ocean is caused by the ocean waves, right? So I just want to tell you how ocean waves are generated, and they are generally classified by the forces that they create them, and that the forces that flatten them, and divided in two classes. So what is called the disturbing forces. So these are the energy that cause the waves, and mostly, so it's the wind, it's the gravity, seismic activity and landslides that can generate waves. So seismic activity, you can think about, if there is a tectonic movement, then this will create a wave, of course. And then there are restoring forces, which are the ones that try to smooth the ocean waves. And this is basically the surface tension, cohesion. The gravity also tries to smooth the ocean surface. So wind is what is the primary disturbing force for generating what's so-called capillary waves, so and wind waves. So here is a little description how it works. So basically, if you have wind blowing for a certain period of time in a certain location in same direction, it starts to transmit this energy to the ocean waves, to the ocean surface, sorry. And it will start with small capillary ripple waves, and then step by step it will fully develop in what's so-called fully developed sea. And then afterwards it will change as well, so to waves that have a longer period. What is important for SAR are actually the ripples, because these ripples are the ones that are on the same wavelength scale of the emitted pulses by the SAR. So just a little note on this. So of course, I'm not an oceanographer, and the topic is very, very difficult and very, very large. So I could not, of course, cover all the aspects, but the point that I wanted to give you is that you can measure so you can observe the ocean because of the wind and the waves, because these are creating the roughness. So it's not, you see the ocean is smooth, and you cannot, like for land application, it's easier because you see buildings, you see big structure, you see bridges, and then it's easier. But for oceans, it's a bit different. So that's the point I wanted to give you, so that we have the roughness over the ocean, and this is created by the wind and the waves. And another point is, of course, the ocean is not static. So there is a lot of literature about how the ocean movements affects the imaging of the ocean surface by SAR, because you should have learned. So everything that is moving is not really a perfect match with SAR, let's say, because with SAR you have like, you think that everything is not moving, and you are integrating the so-called during the aperture, so the synthetic aperture, and you think that everything is static, but it's not. So of course, if you're interested, there are plenty of books. You can read about it. You can study about it. So the other part that I want to give you, I don't know how much details you got from the previous lectures about polarimetry and what wave polarization is. So I've just very brief introduction about this topic. So the wave polarization is the behavior of the electromagnetic, the electric field that you observe. So the most general polarization is what's so-called elliptical polarization that you see on the left-hand side graph. And this is generated by having the electric field X and Y components not equal. So the waves, so the electromagnetic waves are moving along the zeta direction and changing the amplitude of the electric field, X and Y, and having also a relative phase different from 0 to 90. Then you have the electric field vector, which is giving you there in green, that follows an ellipse while the components are rotating, right? Then this specializes in the circular polarization, and that's the case when both components, X and Y, are equal, and you have a relative phase between the two components that is plus or 90 degrees. That means that, yeah, again, the vector, electric vector field, here in green again, it will give you like, a circle. And this is again specialized in linear polarization, where the components are equal in amplitude and also in phase. And in this case, it's 45 degrees. So you can have also linear polarization horizontal, which means you only have the X component of the electric field, and vertical, if you have only the Y component. So so this is the basic information about electromagnetic wave polarization. So the most used in SAR is linear polarization, because it makes the life easier for people building the sensor and also for managing the data. But there are currently satellites SAR also that use circular polarizations. So today we focus mostly on using linear polarizations. So what happens when the SAR then transmits the incident wave? So what it happens is that the scatterer, so the scene that you are observing, it changes the polarization state. And what you get back is a transformation of what you sent. And this transformation is basically given you by the so-called scattering matrix, which is given here by S. And you have, in the case of linear polarization, so meaning that you transmit an horizontal H polarization and you receive H, transmit H and receive V, and transmit V and receive H, transmit V and receive V. So you have the four combinations. So these are here represented in the so-called scattering matrix. And you can differentiate between a monostatic radar and a bistatic radar. So monostatic radar is when transmitter and receiver are in the same location, like you see in the picture here on the right. So you see the radar transmit and receive on same position. And bistatic is when you transmit from one position and you receive from another position. So there are bistatic radars available, but today we focus on monostatic case because it's the most, most satellites are monostatic at the moment. Another point is that each component of the scattering matrix, so so-called complex scattering amplitude. It's composed of an amplitude and a phase. So you might have got this information also from yesterday's lecture about interferometry. So also in polarimetry, we make use of the phase information. It's not only the strength, but it's also how the phase between the incident and coming waves is measured, right? And what is also one point is that actually for the bistatic case, you have the copole, so-called copole scattering amplitude. They are called copole because they are sending and receiving with the same polarization. And there are the so-called cross-pole channels, which means that you send in one polarization and you receive with the opposite. So the cross-pole scattering amplitude values are usually different if you have a bistatic configuration, but they are almost equal, although some exception applies, we will see later, for the monostatic case. So in the monostatic case, you basically have 3 complex scattering amplitudes. Okay, I forgot to mention, if you have questions, just raise your hand and we try to answer your questions. Last point is about how this is important when you observe the Earth's surface. So on the left-hand side, you see some so-called canonical scattering configuration, let's call it, and what is the resulting scattering matrix, right? So you have so a vertical dipole, it means that you only will receive a vertical component and the other components will be null. If you have an horizontal dipole, you get only the horizontal component. If you have a diedral, you will have both copole, but HH and VV are out of phase. And if you have a triedral, you have HH and VV with cross polarization null. And in this case, they are indeed in phase. So I guess you also have heard about the different scattering mechanism you can observe with radar. Here it's kind of recap. So you have surface scattering, which you usually observe with bare soil or sea surface. And these are characterized by having the cross-pole scattering amplitude almost 0. And usually you have the VV component that is larger than the HH component. And the phase difference between VV and HH is almost 0 or 0, which means that if you take the absolute value of the sum of HH and VV, you have a value that is high. And on the right-hand side, you see a SAR image, which is showing you, for example, over the ocean, you get HH plus VV that is dominant among the other components. Then you have the volume scattering, which is in case of forests or buildings, in some cases. In this case, you have that both copoles are high, but the cross pole is usually larger than the other ones. And if you color code these in green, you see, for example, here in the San Francisco Bay, you see that the green is dominant, for example, over vegetated area. And then you have double bounce, right? So double bounce happens a lot in urban areas. These are characterized by HH being larger than VV, and a phase difference equal to pi, which means that if you have the amplitude of the difference between HH and VV, complex scattering amplitude, then this value is high. So if you color code this in green, then you see in the where the arrow points that you have predominant red value over the cities, for example. So of course, what is interesting for us is the surface scattering, because it's what is happening over the ocean, and double bounds for the ship detection that we will see later on. Okay, some other basic information that we will use. So usually to retrieve the geophysical information, the scattering matrix is useful for point target, but not useful for distributed target. And when you want to retrieve information about distributed targets, then you need to vectorize the scattering matrix with a transformation, which is given by here. So the trace of the multiplication between the scattering matrix and C, where C are orthogonal spin matrices. And in polarimetry, you will hear about two of these orthogonal spin matrices. One is called lexicographic, which is given by CL. And the other one is the Pauli representation, which is given by CP. Here are the equation. And if you substitute these in the transformation above, then you get a vector representation of the scattering matrix, which is given by KL and KP. Right? So these vectors are quite useful. And if you want to measure the total power, or what is called the span, of whole components that you receive from radar, this is given by the span. So it's the square modulus of the sum of the three components. Why the vectors are useful? Because with these vectors, then you can create so-called second-order statistics, so the covariance and coherency matrices, which are, so the first is given by C3, and the second one is given by the T3. So here it's a vector multiplication between, the first is given by the vector multiplication between KL and is adjoint. And here you see what the operators are doing. So the asterisk, it means conjugate, so opposite in phase. So the complex value is opposite in phase. And curly brackets, it means averaging. So you need to go, when you want to study distributed target, you need to average around a pixel to get a second order statistics. So that's another representation of the covariance matrix, which is basically putting the HH component in common. So you have, so the C3 will be represented by the matrix that you see there above. And this is quite nice because it gives you already some so-called polarimetric features. So, for example, with sigma, we usually denotate the channel power. So then you have some other features that are the delta and gamma, which are the cross and copole polarization ratio. And then you have the interchannel correlation parameters, which, for example, rho should be familiar to you from the yesterday lecture, because in interferometry you also used coherence. In that case, you have two complex images acquired in different times, and you have coherence. Here, in polarimetry, you have two different channels, so the HH and VV, and you can estimate the correlation between these two channels. Okay, that's some of the parameters here are used for oil spill and ship detection, and that's the reason why I wanted to give you a little bit of overview. Then we have also the so-called eigenvalue decomposition of, for example, the coherence matrix. So you can do it the same with the covariance matrix. So this is quite important analysis if you want to discriminate which scattering mechanism is happening on the observed scene. So from the T3, for example, you have 3 eigenvalues, which normally the first one is larger than the second one, which is larger than the third. And in the case you estimate these values, and only the first one is different from 0, then you can be sure that the dominant scattering mechanism in the observed scene is a single scattering mechanism. It can be one of the 3, but it's only one. And then you can go from this kind of from this case to the most random case, which is when the 3 eigenvalues are almost equal and different from 0. And this is happening when you have partially polarized scatters. And with the eigenvalue, you can retrieve some other polarimetric features, which are given here. So you can estimate the randomness of what is happening in your scene with the entropy, which is basically the sum of the probabilities of each eigenvalues, where the probabilities are given by Pj. Then you can have the so-called average alpha angle, which is telling you, so it spans from 0 to 90 degrees, and it tells you if you are observing an odd bounce or an even bounce, or in the case of 45, if you have multiple bounces. And then you have the anisotropy, which also spans from 0 to 1, and which is less used because it's kind of complementary to the entropy. But just for your information, you can also have this. Of course, another little note, so the time is not enough to cover all the polarimetric techniques. Today we are going to focus on a marine application, but there are also other techniques which are so-called model-based decomposition. So you try to decompose the scattering matrix on some model assumptions and see when it happens, surface, volume, and double bounce. But today are not covered because of the time, and because I want to stop boring you with mathematical stuff and show you some example about maritime applications. Just a little note, so POLSAR is the abbreviation for polarimetric SAR. In a nutshell, you have the radar is composed by having 2 receiver channels and 2 antennas. And as I said, you see the diagram here. That means that you transmit, for example, H, so linearly polarized horizontal, and then you receive at the same time H and V. So this will give you the component HH and HV. Then you switch polarization, you transmit in V, and then you have the VH and VV. And this is how you construct the scattering matrix. So some notation. So normally this mode is either called fully polarimetric or quad polarimetric radar, which is meaning that you get all 4 combinations. So when you get the SAR image, you will actually have not 1 image, but 4. And this is because you are doubling the PRF, so as I showed you before. So PRF stands for pulse repetition frequency, because you have to switch between the H and V in transmit. But you have also the so-called dual pole combination, which means you are only receiving the combination HH-HV or VH-VV, and also the combination HH-VV, which for certain submissions, in some case, this the HH-VV combination is called twin mode. In some other cases, it's called alternating polarization. Some other satellites, you find it calling ping pong mode. So what here important is that the HH-VV combination, which is coherent, which means that the phase information between the 2 polarizations is kept, is not thrown away, requires also a doubling the PRF. And when you double the PRF, you get some side effects on your SAR image. So basically, your swath coverage in range reduced to half compared to a single polarization. And also the spatial resolution is actually twice worse in azimuth, not in range. And so there are side effects. You acquire more information, but at the cost of coverage and resolution, which are 2 factors that plays a role in maritime applications. So to show you the first case, so what I mean by reducing the coverage, so what you can see here is a Google Map overlay of 2 acquisitions from satellite. This is the so-called tandem mix configuration. Is composed of 2 satellites, which for a certain period of time, they were basically flying one from another in a very short baseline, so about 10 seconds, or 76 kilometers, quite near to each other. So the first satellite acquired an image over an oil spill, and the SAR image is given by the frame in red, and you see this dark area in the middle of the image, which is an oil spill. And then the satellite that comes after, 10 seconds later, it observes the scene almost at the same time, so 10 seconds after, and in this case was using the quad pole mode, which then you see that the coverage, so in the range direction, or across track, how you want to call it, it's actually half. And of course, this is a limitation because you see in the polarimetric case that you only cover part of the oil spill. So, and you cannot observe the complete scene. The other effect is so the reduction in the spatial resolution, and this is something that is important for ships. If you want to detect ship, of course, higher the resolution, the better. And again, this is the same. So from that data set, the same ship observed by the first satellite towards TerraSAR-X, and on the map here on top, you see the ship using the single pole HH, which has a resolution of range and azimuth about 1.7 by 3.3. And on the bottom, you see the HH channel acquired with the quad pole mode, right? So the effect of the loss in resolution, you can see it, right? So here the two pictures are, so the radar signal strength is color-coded from blue to red. So red means you get very high backscatter. So most of these points are kept. So you see that there is quite a good match, at least in the left part of the ship. But on the right part of the ship, you see that there is some loss in this pixel with strong backscatter. And so this is not a very large ship. It's a ship that's about 67 meters, and the width is 14. So on the right-hand side, you see, so basically the plot showing how the scattering change on top along the range profile. So summing all the columns and then just plotting it. And in red is the single pole, and in cyan, the quad pole. You see, so the peaks are almost corresponding, but you have some loss, for example, in the right-hand part, especially in here. And the same you can do it also in the azimuth profile. So this is some side effects that you have to take into account when using pulsar. So some basic information also about which modes you can have with SAR. So basically you should already have this information, but SAR is very flexible instrument because it allows to have either large swaths, so large coverage with low resolution, or very high resolution with a little coverage. So just to have some acronyms or some commonly used terms. So you usually have, so the ScanSAR mode is the mode where you have very large coverage. Here on the right-hand side is the red one. And basically there are so-called ScanSAR wide and normal ScanSAR. And with these modes you can cover, here you cover basically the German byte, so completely. But these modes have so-called low resolution. So you range from 40 meters, the wide mode, to 18 meters, the normal mode. Of course, these modes are specialized, or this resolution and coverage is specialized in the case of TerraSAR X, but you can find the same for other SAR missions, also with Sentinel-1, or with Cosmos Skymed, with RadarSat. So they are mostly common acronyms. Then you have the standard mode, which is so-called strip map, because it's basically the satellite is moving and is scanning in a strip. And this is somehow giving you a good balance between resolution and coverage, because you have, for example, in TerraSAR X, swath width of 30 kilometers, and you can go down to 2 to 3 meters resolutions. And then you have the spotlight mode, which is the very high resolution. But you see, you cover very small portion of the Earth. So the modes that allows you to have also polarimetry are the strip map and the spotlight. Especially the strip map, you have the different combination of dual poles. So you will have the HH-HV combination, the VH-VV combination, and the HH-VV combination. For Terrazar X, the spotlight will only give you the HH-VV combination. So in which applications are these modes used? For example, the Scansar are normally used for oil, for ship, for coastline, so iceberg, so you have very large coverage. Strip map are also used for oil and ship, so also for wake, iceberg, and also specialized for wind and waves estimation. And then, for example, there are, for Terrazar X, an experimental mode that is called DRA, that stands for dual receive antenna. So the antenna is split in two to acquire either quad pole or the long track interferometry. So you have heard about this technique. And the DRA mode is something that is used for oil and ship, or also for current. So let's dive a little bit on the topic about oil spill. So first of all, definition of oil spill, what it is. So oil is a very generic term, so it's really denotating all the kind of petroleum products that you find, and especially crude oils are made up of wide spectrum of hydrocarbons, so ranging from very volatile component to very heavy components. And what is defined as oil spill, as you see here, is a violent spillage due to human activity. And this means human activity can be anything. It can be a platform accident, a tanker that is sinking, or some routine operations that are done by the oil tankers. And I don't have to tell you, but so these are a very strong threat for the environment. So that's why it's very important to monitor oil spill and give the information about oil spill extent, where it's moving, because then the right measurements can be taken to limit the damage. What sources of oil spill we have? So we can have oil spill either on land or on ocean. So actually on land, on the left-hand side, you see a big portion of oil spill on land is happening. It's also an environmental threat, but in that case, it's easier to manage. So the response in case something happens, because you're on land, so it's easier. So unfortunately, also a big portion it happens on oceans, and there are different reasons. So you see here some statistics. So 20% is about tanker operation and accident, 6% tanker operations, 6% tanker accidents. A little amount about terminals and work sites. And on the right-hand side, you see an extraction of the largest oil spill in history. And you see where, you see the name in this list. But what I want to point out is that actually, if you see this list, so accidents that are involving tankers rank top in the number, but not in quantity. So that seems strange, but this is not something that happens once, it's happening continuously. So small spillages are there. And it's also not very easy to estimate the amount if this is happening due to routine operations. Some of these oil spills, they are actually quite famous because they were announced in the media, because they were like threatening some specific geographical area, or like, I mean, you probably have heard about the Deepwater Horizon oil spill, but there are many others involving platforms. And besides, so what is an accident and causing an oil spill during an accident, there are also 3 types of routine ship operations which pollute the sea with oil or oil-water mixtures. These are so-called ballast water, which mainly involves tankers, so not passenger ships or not pleasure ships. Then there is also tank washing procedure. This also involves mainly tankers. And also the engine room effluent dischargers. So tankers basically are doing this because they want to save time and money, because usually you should reach the port and go to the facility and clean your ballast water and so on, but save time, you just throw it in the ocean, and that's it. So then you save time and money. Of course, what has been done to prevent this, we have from one side, we have prevention with conventions and regulations, and you have, of course, monitoring and surveillance, because then you need to ensure that these regulations are kept. So on the left-hand side, so the most comprehensive regulation about maritime prevention of pollution by oil is given by the International Maritime Organization. It's called MARPOL, and specifically the Annex 1. So here you see what is actually allowed and what is not allowed by the different types of ships. So on the top you see like for ships which are larger than 400 gross tonnage, and for oil tankers gross or bigger than 150 gross tonnage, you cannot discharge more than 15 parts per million of oil in your oil water mixture. And this is allowed, so the maximum is allowed when the ship is en route and 12 miles from the coast. And this convention is also defining the so-called spatial areas. Spatial areas which are Mediterranean Sea, Baltic Sea, Black Sea, and so on. You see the list there. In spatial areas, the deliberate spillage of oil in any quantity is forbidden. So then you have also the discharge of oil from cargo and ballast space. This is a little bit more restrictive, and is only applying for oil tankers, which are larger than 150 gross tonnage. And the regulation says that the ship has to be 50 miles from the land. It should be en route, and you cannot discharge more than 30 liters per nautical miles when you are moving. So then there are special regional convention, like for example in the Baltic Sea you have the so-called HELCOM convention, or Helsinki convention, which are more restrictive. And the way how you can ensure that these regulations are obliged, it's via monitoring and surveillance. And satellite is a great help on this side. And so the European Maritime Safety Agency, so the EMSA, has established since more than 10 years a program that is called Clean CNET, which is the European satellite-based oil spill monitoring and vessel detection service. So all the members of EU through the EMSA can make use of this service. So you have the offer is they can do routine monitoring. So images are planned to cover certain areas. And you can have emergency responses. So if something happens, so the service comes into play and help the member state. And then there is also specific pollution monitoring operations, which you plan for example, some aircraft surveillance over a specific area, or if a member state has a doubt of an oil spillage going on, so they can come into play. Of course, so EMSA is part of Copernicus, and of course is making use a lot of Copernicus data. So mainly the service is based on synthetic aperture radar images, but they use also optical image for recognizing ships, for example. And of course they use Copernicus data and Sentinel-1. What sensor do we have? Which remote sensing technique are used for oil spill? So here is a little table summarizing what is available. So you have two columns, actually three columns. So the type shows you which sensor and some information that are useful for oil spill monitoring. And then the division between what are the optical sensor doing and the microwave doing. So in the optical you have visible sensor, infrared, ultraviolet, laser fluorescence sensor, and in the microwave you have the microwave radiometer and also SAR, so the synthetic aperture radar, and side look airborne radar. So this is SLAR is normally used on airplanes because it's easier, the processing. So the aircraft, while scanning, it's also giving the image live. So then the operator can see if there is an oil spill or not. So of course there are differences between these sensors, in which weather condition they can operate. So you have some that can operate without clouds, like the microwave operates without clouds or with clouds. And the optical, you mostly need a clean sky Otherwise, you cannot observe the scene. And 24H operation means you can use this sensor day and night. So some can do day and night, some not. Some have high resolution, some have lower resolution. Some have small to medium to high coverage, we have seen. Some can provide the oil thickness information. Some cannot. For example, SAR cannot retrieve the information. Already told you that you get, so the microwaves are not penetrating into the oil. So, and that's why you cannot also doing the classification oil. You cannot say which type of oil it is. But other techniques can do it. So like the laser fluorescensor, for example. And yeah, some have some types of false alarm, some others are not. So this is, yeah, a summary more or less of what is available. Of course, SAR is the one that is most generic, but cannot do everything alone. So actually you need help of other sensors. And this is what actually happens during the routine operation. So SAR is actually used as an early warning system. So you pass over by the satellite, you have some hotspot identified, and then the patrol control, or the maritime patrol control, will either fly over the area or go by ship and check what is happening. Some examples, finally. So here you see two pictures comparing an oil spill with, on the left-hand side, you have a multispectral optical image acquired by the MODIS Aqua satellite from NASA. And this was acquired during an oil spill on an oil platform in Timor Sea, so close to Australia. And the oil in the optical image appears sometimes, in this case, dark blue, but sometimes you have this shining effect, which gives light gray vision of the oil. So this depends on the sun glint, so how the optical satellite is looking at the scene. And on the right-hand side, you see the same image, the satellite SAR image acquired by TerraSAR X, covering the area given by the dashed line. So a couple of hours after, I guess, yeah. So 3 to 4 hours after the optical image. So you see they quite match to each other. Of course, optical, it's an easy, yeah, it's easier for human to recognize what is happening there. And on the right-hand side, so the oil spill area, I can already pre-announce you, is where you have this large area of low backscatter, so this dark area in the image. Then another example, this, again, comparing the optical with SAR. So on the left-hand side, the image acquired by the MVSat Meris multispectral sensor during the Deepwater Horizon oil spill, so in the Gulf of Mexico. This was very, yeah, a large accident, also, yeah, given by the media, a lot of information. So this was one of the first image after the event. And actually the SAR satellite that is on the right-hand side was actually acquired before the optical image. And of course you see in the optical image, you see clouds in the right bottom corner of the picture. Luckily, was not covering the oil spill area, which here, for example, is giving you this light gray color. And then you also see, comparing the two images, that so you have this atmospheric front that is moving south, east to northeast to northwest, which basically moved this big, polluted ocean surface towards the ocean, the land coast. So this is why having multiple observation, also using multiple satellites with multiple technique is always good, because in this case could be better prevent what are the action to take into account. And as a matter of fact, so the oil spill was, the deep water horizon oil spill was going on for days. And here, just to show you like another SAR image that was acquired later on. So it was 3 months after the first event. So, and you see, for example, in this zoom, so the pollution control agency, they tried to fight against the oil moving towards the coast, creating this artificial barrier. But so the accident was so large that they could not actually prevent the aged oil to approach the coast. Yeah, so that is mostly what you can do with remote sensing. Let's dive a little bit how this is happening and why you see dark as an oil spill is happening in a SAR image. So these illustrations gives you a complete picture of what is happening. So you have oil, so we have already seen that you have the ocean with its roughness, and when the satellite is transmitting the pulse and receiving the pulse from clean ocean sea surface, then you have some backscatter received from the satellite. While when you have oil, which is this black part in the picture, this basically, the oil is smoothing the surface, and this means that the radar energy is scattered away from the sensor, so you receive less backscatter. What time we do?
More or less now, 10 o'clock.
10 o'clock?
Più o meno, sì.
Okay. I don't know, what do you prefer? Do you prefer to go more into details now about this, or have coffee break now, if you...
And also ask questions, because so far you didn't have much interaction with Domenico.
I do have a question,
Please.
please. Before you talked about the oil spill, right? So the question is like, how fast can you detect an oil spill?
How fast?
Yeah, because like the satellite can go, I think, in 1 hour, make it full circle.
Not.
1.5.
So I mean, in 1 hour it will be like the damage is done if there is a spill. So how is the technical? How is the procedure in this case?
Sure, you are talking about an accident, right? So you have
an accident. I mean, the satellite detects it. So what is
So the procedure that is, for example, applied by EMSA, it's the so-called near real time. So basically, if there is an accident, the first satellite overpass is taking a picture. This means that from the SAR acquisition to the delivery of the information to the end user, like the maritime petrol control, it takes about 20 to 30 minutes. This is what EMSA, for example, is delivering to the member states. So the near real time for both oil and ship detection, it's like you count the time from the satellite acquisition to the delivery, it's about 20 minutes. So,
but of course, you're not sure that there has been a satellite acquisition just after the oil spill.
Yeah, that's of course. I mean, that's why I said after the first satellite overpass, it acquires an image, and then from that means it depends also where the oil spill is happening, which satellite is using, because normally, so what the SAR acquires is the raw data. So the raw data then needs to be sent to the ground to be focused. So the raw signal is then focused in an image, and from that point on, you can run the algorithm about oil and ship, and then deliver this to the end user. So, of course, this depends also on the ground station coverage. So as different partnership with different ground station operators around the world. So, and I guess for Sentinel, you have also this relay with.
But just one concept I want to say: the fact that the one satellite orbits 1.5 hours doesn't mean that every 1.5 hours a satellite is passing on the same spot, because the Earth rotating. So in the case of Sentinel-1, for example, if you are only Sentinel-1A, it takes 12 days before you have acquisitions all in the same place. If you have Sentinel-1A and B, then it's every 6 days. But thanks God, there is not only Sentinel. There are Sentinel, RadarSat, Cosmos Skymet, etc., etc. So EMSA is collecting the satellite acquisition from all the different satellites. And then, of course, it's much more frequent.
I mean, you have also to distinguish the repeat pass, which is really the satellite, because satellites are orbiting in LEO orbit, so in polar orbit, right? So with the same exact geometry, it's what Francesco told you. So you have 12 days, which means the same geometry. But because SAR is quite flexible, you can steer the beam of the antenna, right? So you can, okay, not the case of Sentinel, because it's acquiring always with specific mode, but other satellites, like Cosmos Skymet, RadarSat, you have different acquisitions. So the coverage, the revisit time reduces. So you have like 2 to 4 days, more or less.
Let's say that for this type of acquisitions, you can also combine different images which are taken with different incidents.
Yes,
it's not like interferometry. Yesterday we saw interferometry. Then you need always exactly the same geometry.
No, that's different. So
in this case, even if you have a
you can change the let's say the acquisition geometry of the satellite. So do you want to have a question? Do you want to have a break?
I think so.
Okay, then let's have a break.
So 15 minutes break.
15 minutes break, okay.